Good day, everyone. My name is Renee Foe, Senior Product Manager at Advanced Cell Diagnostics. Welcome to the first series of 3 webinars focused on our RNAscope products. The title of this series is Step for Success with the RNAscope Assay, which is focused on our manual assay products. Future webinars will cover specific manual assays and automation. It is my pleasure to introduce Dr. Jacqueline Akich, our Senior Product Application Specialist, who has had extensive experience in molecular and cellular biology. Jacqueline supported RNAscope and a variety of its applications for over 2 years. A few notes about this webinar. As the audience, you will all be automatically muted. If you would like to ask a question, please wait till the end and select the chat button in the WebEx to ask questions to the host and presenters. Apologies in advance if we are unable to answer your questions. We will be following up with you offline. And lastly, towards the end of the seminar or after the seminar, you'll be receiving a thank you email, which will have a link to a survey, and we would appreciate your feedback. Thank you.
Thank you, Renee, for that introduction. Today we'll be focusing on manual assay users, and the following will be the topics for discussion. We'll discuss how RNAscope technology works. We'll discuss how to get started with RNAscope in your laboratory. We'll share some tips and tricks on running your assay, review some frequently asked questions, and set aside time for questions and answers. So for the next segment, I will be reviewing RNAscope technology. The RNAscope workflow has various steps, and I'll walk you through the workflow from left to right, as in the slide. The first step is permeabilization of cells or tissue. Tissues are typically already fixed on slides and are permeabilized through pretreatment to access the target RNA. The next step is hybridization by binding of the double-ZZ probes to target RNA. In some cases, you'll have 1 RNA or 2 RNAs that are being probed. The next step is binding of preamplifiers to the double-ZZ probes, and the preamplifiers are followed by binding of amplifiers, and then concluded by label probes that are usually tagged by either chromogenic or fluorescent labels. The resulting signal is a punctate dot, and the dot can be visualized by either light microscopy or fluorescent microscopy. You can score your images semi-quantitatively, and we will be discussing that later. The next is a review of the double-ZZ probe design. The ZZ probe design has 3 elements. In the lower region, there are 8 to 25 bases, and in the upper region, there's a 14-base tail sequence. These 2 regions are divided by a spacer region. For RNAscope to work, the ZZ probes come in pairs. As you can see in the top region, we have now a 28-base sequence that the preamplifier binds to. And on the lower region, there's a 50-base region, which is complementary to the target sequence. The standard RNAscope design consists of 20 ZZ probe pairs, and the standard region that we design the probes is 1 kb region. This results in 20 pairs of 50 bases. In the event that your RNA is degraded, as shown here in the yellow line, RNAscope can still work and result in a punctate dot. This makes RNAscope highly specific and robust for signal amplification. All this work has been published in the Journal of Molecular Diagnostics that you can refer to by downloading from our website or from PubMed. We also have a series of publications now that you can review for your particular application. These applications are also segmented in our website based on the application of your interest. You should review our website for all our publications. The next is RNAscope workflow. Before I discuss RNAscope workflow, I would like to introduce you to the products that we have. The first product is RNAscope 2.0 HD Brown. This is a chromogenic product that utilizes DAB and HRP chemistries. You can use this with probes in channel 1, and they're annotated as C1 probes. The next is the 2.0 HD red assay. This is also a chromogenic assay that utilizes the fast red and alkaline phosphatase chemistries. You can also utilize probes in the first in channel 1, known as C1 probes. The 2-plex dual chromogenic assay utilizes HRP green and fast red alkaline phosphatase system. The probes are in channels 1 and 2 and are annotated as C1 and C2 probes. The final assay that we have available to you is the RNAscope multiplex fluorescent assay. This assay utilizes fluorophores in the wavelength similar to 50, Psi3, and Psi5. This is typically an up to 3-plex assay, and the channels available are 1, 2, and 3, annotated as C1, C2, and C3 probes. The next, we'll discuss the RNAscope workflow as you would experience if you're working with this assay in your laboratory. The standard workflow consists of 4 steps: pretreatment, hybridization, amplification, staining, and detection. As shown here, the pretreatment consists of 3 different steps. This is an example for formalin-fixed paraffin-embedded samples. In formalin-fixed paraffin-embedded samples, you will require 3 pretreatments. The first will be pretreatment 1, which is a peroxidase blocking step. Next is an epitope retrieval step that includes boiling. And third is a protease step, which is required for unmasking the target. The next step is target probe hybridization that typically requires about 2 hours, followed by a wash. This is followed by preamplifier binding and a series of washes and amplifications. The final step is binding of the label probe, and the label probe is typically tethered to a chromogen. For our system, as we've discussed prior, could be DAB, HRP, or fast red alkaline phosphatase system. This is followed by a wash step, detection, and counterstaining with hematoxylin. For the chromogenic assay, the detection can be performed by using a standard light microscope. I'd just like to point your attention to where you can find all of our assays in our user manuals from our website, and I'll point that to you later in the talk. The next workflow is the fluorescent assay. And the thing I want to highlight here is that the workflow looks similar, but there are some key differences. One of the key differences is the fixation and the preparation step. This is an example of a fresh frozen workflow. For the fresh frozen sample workflow, you typically would fix the sample, dehydrate, and only perform pretreatment using protease digestion. You will not require pretreatment 2 for this particular sample. The following step is similar to what we've seen before, which is target probe hybridization, washing, preamplifier binding, and a series of amplification steps. In the label probe hybridization, this step is tethered to a fluorescent label. This is followed by a wash step, counterstaining with DAPI, and the image is viewed under a fluorescent microscope. The key importance of RNAscope assay is that now we have an opportunity to segment the assay into 1 or 2 day assays. In the 1-day assay, as highlighted here, you perform sample preparation, pretreatment, and the actual assay all in 1 day. In the 2-day assay, you will perform sample preparation and pretreatment on day 1 and RNAscope assay on day 2. Some of you are already aware of our protocols that includes part 1 and part 2. In part 1, we review the sample preparation and pretreatment, and in part 2, this is the actual RNAscope assay that you will be performing. You can review this manual before starting your assay to determine which optional stopping points you can utilize to run a 1-day or 2-day assay. So now that we've reviewed RNAscope technology and the workflow, we'd like to discuss how to get started with RNAscope in your lab. We have consolidated getting started into 3 easy steps. The first step that we recommend is to look at your checklist. Checklists are available in all manuals for you to review the required reagents and materials before you run the assay. We We also recommend you use controls, and we will be discussing some of these features later. The third step is to optimize your assay. We have a link that's dedicated just for the Getting Started page, and you can visit this at acdbio.com/go for more information. To review your checklist, we have compiled a few items that we think are important for you to pay attention to. Some of this equipment and reagents are already available in your lab, or you will be receiving if you don't already have your reagent kit as an example. However, we will go through step-by-step instructions for some of the key features of some of these materials that we know will result in success of your assay. The first is using a hot plate. This is a typical hot plate setup, which is very familiar to most of you. Typically, we'll have a beaker, a hot plate, and a pretreatment tube buffer. And this is, again, primarily for an FFPE pretreatment as an example. The key points to pay attention to in this step is the boiling time and the temperature. We have highlighted the requirements for boiling and temperature in our manuals. As an example, for FFPE samples, we recommend 15 minutes boiling and temperature not to exceed 101 to 104. This is very important for your assay, as overdigestion could occur if you overextend these two parameters. You also should make sure that during boiling to cover the beaker with a foil, not to allow any boiling over. The next is the RNAscope reagent kit and contents. Most of you are probably familiar with the old setup for our reagent kit. The main contents of the reagent kit are pretreatment reagents, RNAscope detection kit, and wash buffer. What's not included in the reagent kit are probes. However, this reagent kit and the information that I would like you to understand are all part of this discussion. For the probes, you should warm at 40 degrees for 10 minutes before use. And for the wash buffer, you should warm at 40 degrees for 20 minutes before use. These two reagents will typically precipitate either during shipping or during storage. Following customer feedback, we have now introduced new packaging for our reagents. As you can see on the right, we have color coding, and we have also highlighted the temperature for storage and also the expiration date. The next is the HYBEZ hybridization oven system. This is a must-use item for your assay. It has been consistently validated by our scientists to determine it as the best hybridization system for use with RNAscope. With the hybridization system, you will get a few components with the package. The first is the humidity control tray. The next is the slide rack and a humidity paper. The humidity paper should be wet before use. This ensures a constant control of both temperature and humidity. I can assure you that if you use this system, you will have optimal RNAscope results. For any questions regarding the HYBEZ oven, please contact your sales representative so you can acquire this system for your assay. The next is accessories for washing steps. Most of you are probably already familiar with the TissueTech washing tray. This tray is utilized for washing slides as shown here, and the protocol that we have introduced is also in the manual. To the right is the Easy Batch slide processing system. This system is convenient since slides can be locked into the slide rack, which is the off-white item, and it comes with a wash tray. You can use this system throughout the assay without removing your slides one by one as you would with the TissueTech washing tray. If this is convenient for your workflow in the laboratory, I recommend this as an alternative for your washing and hybridization steps. The next segment we will discuss is how to qualify your samples using controls. To qualify your samples, I will first start by introducing you to our semi-quantitative scoring criteria. This criteria has samples rated from 0 to 4. This is an example of a HeLa cell pellet, and the typical high score for HeLa cell pellet is 3 and 4. However, when you're running RNAscope, we always ask that you introduce a negative control. And the negative control typically scores as 0 or less than 1. To the right, you can see that the scoring criteria is dependent on how many dots are available per cell. And below, you can see that a score of 3 shows the amount of dots per cell that are indicated. This is a schematic of how to qualify your samples. I'll urge that you use this schematic as a way to start your assay and perform sample qualification whenever you're starting your assay or using new samples. The first step is a technique check. The technique check requires that you use control slides. In this case, I've highlighted HeLa control pellets that are commonly used by most of you. Others who are using mouse samples, we have the 3T3 cell pellets. However, in general, you should use DAP-B as a negative control and PPIB as a positive control, and these are just examples. Once you use these two probes, you should run the assay as usual as highlighted in the manual. You should perform a quality control check. In this example, we're looking at PPIB and DAP-B. If PPIB is greater than 2 and DAP-B less than 1, as shown here, you should proceed to sample and RNA quality check. This will be specific to the sample you're using. We recommend that you always start with standard conditions. You should perform the assay with DAP-B, negative control, and PPIB as an example of a positive control. You should perform the same exercise by doing a quality control check where PPIB is greater than 2 and DAP-B is less than 1. If this criteria passes, you should continue to run your target probes. However, if there is a failure in any of these two checks, you should verify the technique and also check your RNA quality. If your RNA quality is a question, we recommend that you run RNAscope with new samples and perform a quality control check again. Also, the other recommendation is to perform an assay optimization. This is a schematic to just reiterate what we just discussed. So the first step would be to perform a sample qualification. You should stain the slides with control pellets, perform a quality control check, depending on what positive control you have. If the test fails, you should retest the invalid results. If the test passes, you should perform a sample check by going through the same exercise with positive and negative controls. If this passes, you should run your target markers. If it fails, perform optimization and perform a retest. If you're having some difficulty in understanding how to proceed, please contact us in technical support and we can provide you some guidance. However, you should still optimize your assay. So how do you optimize your assay? To optimize your assay, we have also consolidated your steps into 3 easy steps. The first step you would have already performed, which is performing standard conditions. In the standard conditions, a few observations are usually highlighted based on our experience. You will observe 2 conditions: high background, which is a result of over-digested samples, and this is usually because samples are underfixed. Sometimes you will find that you do not see a signal or the signal is weaker than you expected, and this is usually because the sample is under-digested and perhaps overfixed. To determine how to optimize your assay, you should perform 2 steps. One will include adjusting pretreatment 2, and the next adjusting the protease digestion, which typically are pretreatment 3 or 4. In this pretreatment 2 optimization, there are 2 conditions that you should work on. If your samples are underfixed, in this case, we're showing a standard procedure where 15 minutes are required for boiling. You should reduce your pretreatment time. If the samples are overfixed, to access that target that you expect to be higher, you should increase your pretreatment too. This criteria is similar for pretreatment 3, only that the time we recommend for pretreatment 3 is 30 minutes. At this point, you would need to reduce your pretreatment 3 from 30 minutes for underfixed samples and increase pretreatment 3 for overfixed samples. If you're using samples with cultured cells, please note that the pretreatment conditions require some dilution. We have all these conditions and pretreatment suggestions in our manuals and technical notes that you can find in our website. You should also note that for pretreatment 3, rather than using the hybridization oven, you would require to perform your pretreatment at room temperature. If you were to perform pretreatment 3 with using the oven, you probably would observe overdigestion. So we recommend that you pay attention to that, the temperature requirement for fresh frozen samples. So here I'm going to discuss some of the troubleshooting issues that we have observed. And we just want to walk you through some of the common issues you'll be experiencing if you have a failed assay. This is an example of a xenograft that's paraffin, the formalin-fixed paraffin embedded. And the first step that was performed with this xenograft was to perform standard conditions. The standard conditions produced a result where the negative control had high background, as you can see here, and the morphology was destroyed, suggesting that this is an overdigested sample. To perform an optimization, the sample was pretreated with a much lesser pretreatment condition. In this case, it was 8 minutes pretreatment 2, as shown here to the right. I'm looking at the negative control.B panel. In this panel, you can see that the morphology has been retained, and the staining pattern of the positive control is great. At the same time, the sample no longer looks overdigested. These are some of the tips that we would like for you to follow when you're working with your assays and your samples, to observe the background, the nature of the background, and understand how to resolve these particular issues. We have a technical troubleshooting guide that you can find in our website, and this is a new item that we would like to direct you to when you're performing your troubleshooting. This is an example of a successful RNAscope result. And what I'd like for you to do is use this as a benchmark for grading how our RNAscope performance is in your hands. This is an example of a 2.0 red assay. However, you can use this criteria for all our assays. You should find that the negative control is clean, the positive control should have robust staining, and the target probe should be specific. If you see this result, you should proceed to the next sample or continue with your assay as you prefer in your laboratory. So for troubleshooting tips, I want you to highlight some of the factors that we know affect the assay performance. The first one is fixation conditions. Fixation conditions create a challenge for your use because samples can be underfixed, overfixed, or sometimes you don't even know the fixation conditions of your samples. Underfixation typically occurs in a lab that is used to an IHC workflow. In an IHC workflow, typically you may fix your samples at 4 degrees and not at room temperature. To mitigate this issue, you should fix your samples at room temperature with 10% neutral Bradford formalin within 16 to 32 hours. Do not fix less than or more than 32 hours, less than 16 hours or more than 32 hours. This could result in underfixation or overfixation. In cases where you do not know the fixation condition, please start with standard conditions as we highlighted previously and understand the state of your fixation before you proceed to your target probe. There are cases where RNA is degraded, and you may not be aware until you run the assay. Some of these cases include, as I just highlighted, an underfixation condition, as well as if you are working with archival samples. For this, we recommend that you perform the quality control check, as we just discussed, and also you should understand that if you perform the RNAscope assay with the quality control with the tissues that are with archived tissues, you may find that RNA is not present. If RNA is not present, we recommend that you acquire new samples. The next factor is hybridization conditions. Many of you already have different hybridization systems in your laboratory, and they perhaps work very well with other systems. However, for RNAscope, we have validated the HYBEZ hybridization system only. This is because this assay requires a controlled humidity and temperature control. Sometimes some of the hybridization ovens do not have these, especially the humidity factor. So we suggest that you use the hybridization oven at all times when you're running RNAscope. If your samples are drying during the assay, it's perhaps due to workflow issues. If you're observing workflow issues, please review our protocols for drying samples and adding reagents. The other factor that causes drying is the use of different hydrophobic barrier pens. While we do not know why our assay works well, why the image pen works well with our assay, we know that we validated other hydrophobic barrier pens and found that sometimes they lift off during the assay. The image pen is the only hydrophobic barrier pen that has shown to sustain throughout the assay. We therefore highly recommend and suggest that you only use the image pen during the RNAscope assay. You should also pay attention to how you add your reagents to avoid drying. The amount of reagents we recommend to hold through the optimization and washes is very key to the success of your assay. Do not add less reagents throughout the assay since you will see drying. Here is an example of some of the troubleshooting issues you may observe. This is an example of fixation conditions. To the left, you see a 24-hour fixation, which is the optimal fixation condition. To the right, this is a 3-week fixation, which is considered overfixed. Looking at the same target in the brain sample shown here, you notice that the optimal fixation shows robust staining, while the overfixed condition shows weak staining. To mitigate this issue, we perform increased pretreatment conditions, and we've highlighted how to do that in the optimization slides. The next condition here is under fixation. This is rat fresh frozen intestines, and we're using the same probe, rat PPID. In the top panel, you see that the staining is weak and the morphology is destroyed. When you perform this assay as we recommend, especially for the fixation conditions for fresh frozen, you note that the staining for positive controls looks great and the morphology is intact. We recommend that you review all these troubleshooting issues in our troubleshooting guide. The last one is an RNAscope assay workflow. This is an example of a HeLa cell pellet, and the top panel shows a sample that's dried out. The result is nonspecific background that may look like dots or sporadic staining. You can also see that clearly this sample has dried out. To avoid drying, please add the recommended amount of reagents and use the image hydrophobic barrier pen. In the event that the hydrophobic barrier leaks, your sample will dry out during the assay. And as you can see, the result is a clean background in this sample. I would like to highlight you to some of the tools that we have for you for optimization. Here is a pretreatment guideline for FFPE samples. You can see the highlights of how to fix the samples and how to pretreat the samples. Importantly, we have some guidelines of the various tissues you may be using, whether mouse, human samples. In Table 1, we also have guidelines of how to perform pretreatment optimization. You can see that we have conditions recommended to start with for mild, standard, and extended conditions. In extended conditions, for example, this is where your sample may be overfixed and you may want to increase some of the pretreatment conditions. In this case, pretreatment 2 is increased to 30 minutes. I'll now review some of the frequently asked questions that we get through our technical support channel. One of the questions is how RNAscope is compatible with different tissues. We have compatibility with FFPE, fresh frozen, fixed frozen, and cultured cells. For automated assays, we are primarily supporting FFPE tissues. You can refer to our user manual selection guide for technical support, downloads for our manuals, and also measuring and determining which protocol you need and which assay goes with the samples that you have. Another question is the key differences between RNAscope and IHC. In IHC, after epitope retrieval, there is a cooling step before introducing antibodies after blocking. In RNAscope, this cooling step is not required. But we have seen that when this is performed, samples are over-digested and you see high background. We recommend that after this step in RNAscope, as in our manuals, simply take the slides, put them directly in room temperature water, wash, dehydrate, and proceed to pretreatment 3, as in the user manual part 1. You can find all frequently asked questions in our website as well. We'll now review guidelines to follow with RNAscope assay. The first most important guideline is to read the manuals and perform the RNAscope assay exactly. Do not alter any steps. If you have any questions about steps that you're not sure about, please contact us in technical support. You should utilize optional stopping points if you find that you need to stop at some point in your assay. Do not proceed with the assay if you feel that you cannot proceed with the assay to the end. We have also introduced a technique of flicking and tapping the slides to allow adequate drying and not introduce under or over drying of samples. Storage of samples is important to retain RNA integrity. As an example, FFPE samples are required to be stored with a desiccant. You should always use fresh reagents. In a multi-user laboratory, you will find that reagents could be contaminated, affecting RNAscope results. You should segregate yourself when working with RNAscope and use fresh reagents for successful results. Also, as highlighted previously, warm probes and wash buffer at 40 degrees since precipitation would occur during storage. Please remember to optimize pretreatment conditions, especially when you're changing between tissues. The pretreatment conditions for one tissue and sample will not apply for all tissues. Review all our tools and manuals that are available for you for this particular optimization issue. As a summary, we have reviewed our RNAscope technology, and we have reviewed in particular the ZZ probe design, as well as the workflow for manual assays. We have reviewed the getting started tips, which includes reviewing the checklist, performing controls, and optimizing your assay. We have also shown you tips for success with RNAscope assay, especially when you switch tissues. We have looked at how to optimize with pretreatment 2 and 3. For more information, we suggest that you visit the support webpage. Here you can find downloads. You can download user manuals, but I also would like for you to utilize a user manual selection guide. You will find this as an easy tool to select user manuals for your sample type, especially when you're switching between samples. You will find MSDSs, images of control images and what to expect, and also tissue requirement and troubleshooting tips. You can also review our Getting Started page, especially if you're a new user. We have step-by-step instructions of how to get started. You can review frequently asked questions, where you can find questions that may apply to you, specific questions you may have. Our online training videos are useful for you to see how users perform a workflow for RNAscope and the steps and intricate details of how to wash and add reagents. For product literature, you can find probes lists, publication lists, posters, application reviews, and we have a new feature, which is the researcher in the spotlight. To contact us, you can reach us via email at support@acdbio.com. You can reach us by phone. Our times are 8 a.m. to 6 p.m. Pacific Standard Time. And you can review all support resources in our website at www.acdbio.com. Here you'll find information on manuals, getting started, FAQs, videos, and product literature, as I just highlighted. With that, I'll entertain questions, and thank you very much for your attention. So while we wait for questions to come through, I have some questions that we get through support that may apply to you. One question applies to FFPE samples, which is, should bake sections be used immediately for RNAscope assay, or can they be stored at room temperature? The answer to that is, once you bake your slides, you can store the samples up to 1 week in a desiccant. This is actually an optional stopping point for you. Once you store them, you can proceed with the assay, but do not exceed 1 week for baked slides. Another question that comes up frequently is, how stable are RNAscope reagents? We now have stability for reagents for up to 9 months, and the probes, we have stability for 2 years. As I mentioned earlier when we were discussing reagent kit, our probes and reagents will have an expiration date in future generation of our products, and you'll see these changes coming through as you order new reagents. There's a question here. Is the fast red kit also excitable by fluorescent light? That's a good question, and the answer is yes. You can use type 3 excitation emission wavelength to view fast red under fluorescent microscope. This is used by many of our customers. Another question here is, do FFPE sections need pretreatment to treatment for fluorescent assay? The answer to that is yes. If you're using FFPE samples, the sample pretreatment is the same whether you're using fluorescence or chromogenic. The only key difference is pretreatment 3, which you will, instead of using pretreatment 3, you will now use pretreatment 4. We have found that pretreatment 4 works well to reduce autofluorescence in our fluorescent-based assay. So to answer your question, yes, you will need pretreatment 2 if you're using FFPE samples, but use pretreatment 4 as the protease digestion reagent. We have another question. I have a question about the minimal boiling temperature for pretreatment 2. What is the minimal temperature for successful pretreatment? So for pretreatment 2, if you're using FFPE samples, we recommend 15 minutes. If you fix your samples as we recommend, 10% NBF, room temperature 16 to 32 hours, you perform pretreatment 2 at 15 minutes, you will get optimal results. However, if your samples have shown background, you should perform pretreatment optimization by reducing pretreatment 2. So the recommended time that we've seen works the best for pretreatment 2 is optimally fixing your samples and using 15 minutes and the temperature at 101 to 104. If you measure this with a thermometer, you will find that this temperature works the best too. So another typical question that comes in is, should our reagents be used with research grade, perhaps RNA-free water? The answer to that is it's not necessary to use RNA-free conditions or water. However, you should practice good laboratory techniques not to introduce external RNAs. But the way the sample preparation is performed, you will not introduce RNAs during sample preparation. The places where RNAs can be introduced is during storage, and this is why we recommend for FFPE samples store with a desiccant to avoid any humidity introduced into the sample. Another question, which is an optimization related question, is if you notice that your sample, your PPIV signal is weak, what do you do? As we highlighted in the optimization segment, you should perform pretreatment optimization. It's likely that two issues are occurring. Either your RNA is degraded or your sample is underdigested. If that's the case, you should increase your pretreatment if your sample is underdigested. If your RNA is weaker than expected, then you should get new samples and requalify your assay. There's a question about tips for reducing autofluorescence. The main key point for RNAscope assay for reducing our autofluorescence is to make sure that your sample is prepared as we recommend. We have noticed that, especially for fresh frozen samples, if the sample is goes through some drying events during preparation, you will notice autofluorescence in the assay. Also, when you're working with multiplex fluorescent assays, you should use pretreatment 4. We have found that this reagent helps with eliminating autofluorescence only because it encourages accessibility to the target and exposes the target. However, your sample preparation protocol is most key to reducing autofluorescence. Also, storage conditions. If you have samples that are stored for too long, you may see autofluorescence. For hybridization conditions, I have reiterated how important the HYBEZ oven is. There's a question here about increasing the temperature. This is a good question. Do not increase the temperature in the HYBEZ oven. Keep it at 40 degrees as we recommend. For those of you that are attending our webinar and have questions based on automation, we'll address your questions offline. And as Vinay said earlier on at the beginning of the webinar, we'll dedicate another webinar just for automation users. I have another question that tends to come in support. That question is, why do I need EcoMount and SuperFrost Plus slides? For EcoMount, this is specific for those who are using 2.0 red and 2-plex assays. What we've seen is when you use other mounting medium, you will notice diffusion. So we recommend that you use EcoMount at all times if you're using both 2.0 red and 2-plex assays. For SuperFrost Plus slides, although they are charged, we have validated this consistently and shown that this allows samples to be fixated on the slide and sustained throughout the pretreatments in the assay. Therefore, I would ask for you to use EcoMount for mounting medium for 2.0 red and 2-plex, and SuperFrost Plus slides whenever you are mounting samples on the slide. If you receive samples that do not have SuperFrost Plus slides, then you should continue running the assay. However, if you have any issues with detachment, please call us in technical support and we can provide you with some guidance. There's another question of whether we should add formaldehyde to reduce background. We don't recommend changing or introducing any reagents to the assay. Therefore, the answer to that is do not add formaldehyde to reduce background. Another question is, does pretreatment 2 and 3 affect morphology of the sample? And the answer is yes. As we discussed in the optimization section, if your pretreatment 2 is not optimal, you'll observe overdigestion, and this will be highlighted by nuclear background, and morphology that's not optimal. So again, to make sure that your assay is running optimally, start with standard conditions, and then adjust your pretreatment conditions accordingly. You can find all this information in our troubleshooting guide. We have some guidelines to help you troubleshoot this issue. If you're storing your probes for a length of time, 3 to 4 months, we just recommend you store them in the conditions that we recommend. If you store them at 4 degrees, as we recommend, I can assure you that 2-year timeline is accurate. You will not have issues with probe degradation. Another question here is, how long is in situ staining stable on sections? So we have two key assays, the chromogenic and the fluorescent. For the chromogenic, I've seen samples sustain signal for quite a while. The key here is to make sure you're using the mounting medium that we recommend and just following the manual as we recommend. And you can store the samples for a long time. For the multiplex signal, you can also see the signal sustained for a very long time. Obviously, try and store the samples away from light, and you can be sure that the signal will be sustained for a long time. If you're experiencing tissues coming off the slides in the event that there's this detachment, one of the likely issues is sample preparation and that you did not use Superforce Plus slides. If this issue is persisting, please call us in technical support and we can provide you with some guidelines. One question that I wanted to introduce to conclude this section is, what is a probe channel in RNAscope terminology? So this is an assignment given to individual amplifiers. So depending on which assay you're performing, we either annotate as channel 1 for C1 probes or channel 2 for C2 probes. This should not be confused with microscope channels. They are basically annotations that we use to distinguish between channels. Just one final question while we wait for any other questions to come in is, can ACD provide probe sequence information on oligo pair locations? In our website now you can find information of the 5' and 3' nucleotide positions of the target probe region and the number of probe pairs generated in that region. There's a question here about a result that was not single dots, but a description that appears to be perhaps clusters, large spots. If you're seeing clusters, this is likely because the copy numbers per cell is much higher. If you go back and review the scoring criteria, you'll notice that the dots can appear as independent single dots or as clusters. So if you're seeing positive signal and your .B background is clean, then that's real signal, and it's basically a factor of the number of copies that you have per cell. So the higher the number of copies, the more the dots would cluster. Well, thank you very much for attending this webinar. Be sure to reach us in technical support if you have any additional questions. And for those questions that we did not reach, we will contact you independently. Thank you so much, and good luck with the RNAscope assays. Thank you.